Hi, everyone. Today we have Nicole Gonzalez from UCLA, who will be talking to us about affine Demazure crystals for nonsymmetric Macdonald polynomials.
Hi, everyone, and thank you for joining us today and or for coming to my talk today, and thank you for the invitation. Um, so, yeah, if you were not here for the little spiel at the beginning, if you have a question, just interrupt me. I will try to keep an eye on the chat, but it's very unlikely. And if you do put a message on the chat, if you can just read it, like interrupt me and tell me, hey, there's a question, read it out loud, that'd be great. Yeah, and so today I'm going to tell you about affine Demazure crystals for nonsymmetric Macdonald polynomials. So if you know a little bit about Macdonald polynomials, or maybe a lot, then you probably know that they're related to affine Demazure modules. And what this talk is basically about is a combinatorial realization of, our combinatorial model for this relationship via crystals. Basically what I'm going to tell you about today at the beginning is a little bit of background on GLN crystals, so that if you're not familiar with crystals, of course, then you have an idea what it's about. Then I'll specialize this down to Demazure modules, and I'll tell you how from these Demazure modules what a crystal is, what Demazure crystal is, both in the finite and in the affine case. Then the bulk of the work that is I joint with Sami Asaf is basically the combinatorial models for these finite and affine Demazure crystals. And then I will tell you how, by taking the characters of these things, you can relate them back to non-symmetric Macdonald polynomials. And how, as a consequence, we get some nice little formulas. Yeah, okay, so let's start. So the first thing I want to talk about are UQG crystals. What are they abstractly? And the idea is the following. So if you have some complex semi-simple Lie algebra, your favorite one, if you just want to think about GLN, that's perfectly fine. Most of the work, or pretty much all the work that I'm actually going to get at today, is type A. So you can just think about GLN if that's good with you. So for any quantum group, any UQG, you have, and you can take integrable highest weight modules, let's call them V lambdas, and they have a natural action, right, by E, F, and K, the Chevalier generators, that give you the structure of the module, right? They're giving you the action of the quantum group. And it's a construction due to Kashiwara and Lustig that you can realize a lot of the combinatorial structure and a lot of the data that you might be interested in by taking a much simpler construction known as a crystal graph, or a crystal basis, or a canonical basis. These are all terms that are very related and essentially are giving you the same information. And what you want to think about, and this is where the name crystal comes from, is that you want to take this module structure and freeze it. And that means you want to take Q, the parameter Q, the quantum parameter, essentially take a limit as Q goes to 0, so that you freeze the structure. And so you end up with a deformation of the original structure, but where you don't see Q anymore. And as a result, the only operators that show up here are deformations of the E's and the F's. And so what is a crystal? For us, really, the only thing you want to think about if you didn't understand or don't care about the module structure is this is really just a crystal graph. It's just a graph, a directed graph, where the edge or the vertices are some sort of finite set. We're going to call that finite set B. And it's known as the crystal base. They're the basis vectors of your module, essentially. And you have some directed edges. Now, these edges are going to be known as crystal operators. That's just a fancy word, but really they're just directed edges that go from one vertex to the other. We're going to note them by EIs and FIs. EIs and FIs are inverses of each other, assuming you're in a defined domain. And they're going to take our vertices, and sometimes they're going to give us 0. And that's okay. And of course, these edges satisfy certain relations. Those relations are exactly encoding so some sort of commutation relations, or sometimes they don't commute. Sometimes they braid, for example. And these relations are exactly the relations that are encoding the module structure. They're the relations of these generators up here, deformed, right? Because we're taking some sort of Q equals 0 limit. In addition, we also have some sort of a weight map that associates to each vertex a tuple of numbers. More generally, this is just the weight lattice if you're in some other Lie algebra. And what this weight is going to allow us to do is to take a character. It essentially allows us to associate to every vertex some sort of monomial, which is where the character theory is going to come into play. So crystal graph, literally just a graph. That's all we want to think about, is a graph with directed edges. Great. Questions about this slide or? Okay, great. So why do we care about crystals, and why are they interesting to combinatorialists or algebraists? Well, the first thing, or I guess the biggest reason, is that they naturally encode a lot of the properties of the module, right? But they're simpler because they're just graphs. But for example, if you want to think about tensor products, modules have a natural tensor product structure, and that tensor product structure is perfectly mimicked and recovered through taking the tensor products of their corresponding crystals. Right, and these are exactly, you get the same branching rules that you get for modules, the same branching rules that you get for symmetric functions, which are just the characters of these modules, right? That's exactly what you're going to be getting here at the level of crystals. And the tensor product is really nicely realized through construction to the Kashiwara. It's very combinatorial, very straightforward, very, very nice. So this is one of the reasons why you might care about, or why you might like crystals. Like I mentioned, they have a notion of character. The character of the crystal is exactly the same as the character of the corresponding module. But often the construction of actually taking the character is very easy, because you're really just taking, as I said previously, you take the weight of every vertex, to it you assign a monomial, which is just, x to the power of whatever the weight of that tuple was. We're here, I'm not sure if everybody here is a combinatorialist in the audience or is familiar with this, so just so that we're clear, if you take an x and suppose your tuple was something like 2, 2, 1, then this is the same as saying x1 squared, x2 squared, and x3. And sometimes if you have a 0, suppose this was a 0, 1, then it would be x3 to the 0, x4 to the 1. So it's just giving you the coefficients of the powers of x. Okay, so let me erase this. Good. And then just as in modules, you have highest and lowest weight elements, right? Which is exactly when the EIs are going to kill you, and when the F5s are going to kill you, that gives you highest and lowest weights. You have crystal isomorphisms, which is just a graph isomorphism where you're sending there's a bijection between the vertices, right? Every vertex goes to another vertex, but the structure of the edges is preserved. So this isomorphism commutes with the edges. And the reason that I particularly care about it is because it admits a really nice combinatorial model, which is what we're gonna, drill into today. Okay, good, moving on. But again, interrupt me if you have a question. Let's talk about GLN modules. Like I said, this is really a talk about type A. So in type A, Lie algebra is gonna be GLN. And our vol group is just going to be the symmetric group, which is going to play a role, as we'll see. So for GLN, the highest weight modules are indexed by partitions of n. So this is some sort of partition of n. And then the preferred, there's many models, but the preferred model that we're going to be dealing with is given by semi-standard Young tableau. So here the vertices of our graph are going to be semi-standard Young tableau of shape lambda. Which again, I'm just iterating this because I'm not quite sure who's in the audience, but a semi-standard Young tableau is just a filling with entries 1 through n of a diagram that is just the partition diagram. And it has certain conditions where you have to be weakly increasing and strictly increasing on the rows and the columns. And then you have the edges of your graph are going to be certain operators. I'm not going to actually define them for you, but there's certain operators that basically eat something, for example, like this, some semi-standard Young tableau, and they change an I to an I plus 1 in the case of Fs, or they change an I plus 1 to an I in the case of Es. Recall that EI and Fi are inverses. So if I just draw the picture with Fs, you can draw it, you can draw the arrows going in the other direction with Es. So it doesn't matter which one you choose to draw. So let's do an example. Suppose my lambda is the partition 2, 0, 0. Then how do I get this graph? Well, I start with the only semi-standard Young tableau that has shape 2, 0, 0. So that's 2 boxes and 0 boxes above it, and has weight 2, 0, 0. So weight 2, 0, 0 means that it's the filling with 2 boxes that has 2 1s. Okay, well then there's only one of it. That's exactly this. And then, again, I didn't tell you how the operators act. but it's a very, easy combinatorial rule where basically you just take some sort of reading word, do some pairing, and act on one of the ones to change it to a 2. So there's a reason I'm acting on this one and not on this one, but whatever. And so then you just act. You just generate everything by taking at each vertex saying, can I act by F1? Yes? Okay, do it. Can I act by F2? No? Okay, then moving on. Then you do the next vertex and so on. You generate this entire graph, and what you get is that, first of all, you see that all semi-standard Young tableau shaped lambda are showing up in this crystal, right? So this would be the crystal for highest weight, lambda equals 2. If we were to do the crystal for highest weight, lambda equals 1, 1, right? Then you get this, this crystal instead, or this graph instead. And you'll notice that in each of these cases, all the semi-standard Young tableau of that particular shape are showing up. Consequently, when you take their characters, which are just taking the weight of each vertex, and you sum it up, you get precisely the Schur functions, right? And this is, in general, a true fact that if you take the character of these GLN crystals, these highest weight GLN crystals, you're going to get the Schur function associated to that partition back. Okay, any questions about this? Is all classical. It's meant to be kind of a very quick intro into what is a crystal, why do you care? Fantastic. Good, so let's talk about Demazure modules and all these Demazure crystal structures that we actually care about in the talk. So what is a Demazure module? So if we take our Lie algebra here, there's a subalgebra known as the Borel subalgebra, right? And it has an associated Weyl group, your Lie algebra. Now there's a natural action of your Weyl group on the weights of your Lie algebra. And what that means is that the Weyl group also acts on the highest weight vectors. There's an induced action. And so what we're gonna consider is not the highest weight vectors directly, but the orbits of these highest weight vectors under the action of the Weyl group. Namely, we're gonna look at these things called extremal weight vectors, right? So it is literally saying, all right, we're gonna take our highest weight vector, we're gonna act by an element of the Weyl group, and that's going to give us some other vector, some vector in the orbit. Our Demazure module then is going to be the module that you get by acting on this extremal weight vector just by the Borel subalgebra. So normally, right, it's kind of a generalization of a highest weight module. A highest weight module, you take your U lambda and you act by the entire Lie algebra. Here, you're just taking your extremal weight vector and you're acting by a Borel subalgebra. So you're not getting the whole thing. You're getting a smaller module essentially. And in particular, these Demazure modules are going to then be indexed by, first of all, your partition, right? Lambda, your highest weight, and some sort of Weyl group element. So if you want to think about Sn, like in the case of the symmetric group, then this is going to give you a partition times a permutation, which is just a weak composition, right? Okay, and then just like in the GLN case, or yeah, in the full highest weight case, a Demazure module or also has a character, which is given by what are known as key polynomials in type A. Oh, there's a question. Okay. Since we are assuming that UQ is semi-simple as an algebra, could we somehow make use of Young tableau to determine explicit formulas for matrix units? Maybe, but I don't know. Off the top of my head, I don't know of an explicit reference for that. Let me think about it. If I come up with something by the end, I'll answer that question more fully. Okay, so moving on. So what, in addition to these properties, these Demazure modules form a filtration for highest weight modules, right? And the reason for that is, if we look at the Weyl group, we can partially order it under Bruhat order, and that allows us to essentially nest our Demazure modules one inside of the other. And if we start, for example, with the most trivial of Weyl group elements, we just take the identity. then we just have the highest weight, because we're saying, all right, we're going to act by our highest weight vector, u lambda, by the identity. You're not doing anything. You're sitting right at the highest weight. All right. So then you didn't go anywhere. Remember that your Borel subalgebra is generated, by the way, by E's and H's. And what that means is that if you're acting on your highest weight by an E, the E is going to kill it, right? And H is just going to leave it fixed, which is why precisely here in the identity case, you're not getting anything else. And then on the other extreme of the spectrum, if we take our element W to be the longest word in the vol group, and then we act on u lambda by the longest word, we essentially end up with this like complete lowest weight, and then we generate everything back. So these Demazure modules you can think of as interpolating between highest weight modules and then just your highest weight vector and giving you everything in between. But of course, you're not just getting random pieces in between. You're getting everything in between that is indexed by an element of your vol group. So there is some control over this. Good. So this is a Demazure module. And associated to it, you also have a crystal. You have the induced crystal that you would get from just taking your big module, since these are somehow pieces in between, and taking the bigger crystal and cutting it up and saying, all right, it's some sort of subcrystal inside this big one, which is exactly what we see in the next slide. So just like the modules are nested, the crystals themselves are going to be nested as well. So for example, in the case where lambda equals 2, 0, 0, right, we have our highest weight as before. At the level of modules, so this is, here we're taking, I should say GLN, we're working with GLN, so then W equals just SN, right? So here we really are looking at just partitions, and then our W's are straight up going to be permutations. So in this case, right, when W is the identity, we're just going to get our highest weight. Then in between the identity and the full crystal, which is just going to be the longest word, in this case in S2 or in S3, so it's S1 times S2. Then we're going to get just one term in between, which is BS1 or BS2. It doesn't matter. S1 and S2 in this case are completely interchangeable. Right, and this nesting of crystals is seen precisely in the graph, where the identity is going to give you just the identity term. This piece is going to give you what you get from taking your highest weight and just acting by S1. Here you're acting by F1. So you take as many F1s as you can, but you don't take any F2s because you just have an S1, right? And that gives you the purple bit. And then now if you allow yourself to take F2s, which is essentially saying take your previous construction and act by an S2 now, then you get the remaining vertices. Fantastic. So then what do we see in this example? What do we notice is that these Demazure crystals are truncations of your original crystal, right? They're always, since they're nested, they're basically, you take your bigger crystal and you erase some edges and you get the Demazure crystal back. And then of course you get exactly what you would expect at the two ends of the spectrum. In addition, if you look at the path, for example, in this middle one, from your highest weight to your lowest weight, which is UW lambda, that path is always going to be indexed by, in this case, f of W, which is f of S1, which is F1. So your path is going to be indexed by that permutation as well. And of course, they're filtered, just like the modules where the crystals are going to be filtered under this brouhaha order as well.
May I ask a question?
Absolutely, please.
So if you were to start with S2 here, you would stay in the green? You would stay at the highest weight?
If I were here, if I were to do S2, exactly, because there's no S2. You can't do an S2 from here.
So sometimes it's a less than or equal, but it could be equal, and then.
Yes, exactly. You're not always going to get something interesting.
Okay.
Yeah.
Thank you.
Mm-hmm. Yeah, and essentially you can see that in the fact that S1 and S2 don't commute, right? And so if this were S1 and S3, then you're guaranteed to have an S1 in the middle and you're guaranteed to have an S3 in the middle. But because S1 and S2 don't commute, the fact that this is the longest word that you're getting, you really have to get like only certain subwords. And yeah, and you can just see that from here, the fact that you're not going to get an intermediate S2 from the longest word. Great. Okay, so then what are the two questions with this construction that we see, right? So the first question is, can we encode these truncations combinatorially? What do I mean by that question? Well, here, if I wanted to know what the crystal for this BW lambda was for this Demazure crystal, I needed to somehow start with the big crystal, the full GLN crystal, and then go back and say, I'm going to erase this edge and I'm going to erase this edge because I started at the highest weight and I traced it out. And somehow I had all this extra information, but I had too much information and I wanted something finer, because I literally had to manually go back and kind of fix the mistake and having too much. So the first question is, can we encode these truncations combinatorially, meaning can we come up with new combinatorics or new operators perhaps that will take care of these truncations for us, that will know exactly when to die and will literally give us a Demazure crystal, not a GLN crystal that I then have to go and manually fix. So that's the first question. And the second question is, can we encode these nested filtrations combinatorially? So here, this seems like a really silly question because you look at this and you're like, well, clearly the green embeds in the purple embeds in the big one because they're the same shape. It's literally an injection. But as we'll see, when we actually come up with a combinatorial version of these Demazure crystals, the embeddings are going to be less obvious because the shapes are going to end up changing. So this question 2 makes a lot more sense once you've seen the answer to question 1. Okay, so let's try to answer question 1 first, which is, how do we come up with a combinatorial model for these Demazure crystals? Right, so for GLN, for the highest weight crystals, our usual structure was just looking at semi-standard Young tableau, right? These were our vertices. And what we want to do is construct a new vertex set for these Demazure crystals. And what we're going to end up defining are these objects called semi-standard key tabloids. Now they're complicated to define, so I'm not going to go into the intricacies of the combinatorics, but let me just say some of the differences. So the first thing is, for semi-standard Young tableau, you're going to look at diagrams that have partition shape, right? Because your highest weight crystals are indexed by partitions. In the case for Demazure crystals, our crystals are indexed by weak compositions, right? Because you're getting a partition times a permutation, right? That's the shape that you're after. So that's what we're going to call A. A is going to equal W times lambda, right? So if we look at, for example, here, A would be 03103. This is the weak composition corresponding to the partition 33100. And when I say weak composition, I mean the fact that we're allowing zeros to be mixed around. And then W would just be the shortest word that sorts A to lambda, whatever permutation you get there. Does that make sense? And so then in that way, the shapes that we're going to be dealing with are just the shape that you get from, or the diagram that you get from shape A, right? And the zeros are kept track of by basically leaving, having kind of a wall here that's labeled so that we know exactly what row we're in, because these spaces are going to end up being very important in defining the theory itself. Likewise, we have different fillings associated to these, right? So in the semi-standard Young tableau case, we had conditions like weakly increasing along rows, strictly increasing up columns, right? In the way that we had to fill it in with entries 1 through n, or 1 through whatever. In this semi-standard key tabloid case, the fillings are going to be more complicated. So we're going to deal with a filling known as not attacking and no coinversions. So these are complicated. Attacking essentially is a condition that involves cells that are either in the same column or in adjacent columns, but they can be many, many rows apart, right? And it's essentially saying if you have a cell here and a cell here, they can't have the same entry. And if you have a cell here and a cell here, they can't have the same entry. Otherwise, they would be attacking cells. So that's this condition. And then coinversions, not going to explain it, but morally, what this is telling you is you're going to look at 3 cells, and you're going to take a reading word. You're going to take you're going to read them from decreasing order, and depending on their orientation, they're going to be okay or they're not going to be okay. And that orientation is essentially dependent on whether the rows are longer or shorter with respect to each other. So it's kind of a complicated condition. we don't need it. All I meant to say with this is that the conditions are harder to deal with, and that they're not just about consecutive boxes, right? And this is a key point, that for semi-standard Young tableau, really, what are you looking at? You're saying, all right, I have this cell, is the one next to it weakly bigger, or is the one above it strictly larger? And that's really it. Those are the only conditions. But here you're really looking at cells like to the left, immediately to the left, and then maybe at every cell, like above it in every row. So it's much more of a global condition on these fillings. So just keep that in mind. Okay, so it's 12
Can
tweaks.
I ask you a very, very technical question?
Absolutely.
So here, this depends on the model you actually take for inversion, co-inversion, and attacking, non-attacking.
Yes.
And I'm aware that there are other models that one can take that are a little bit more Young-like than these one. Could that help your model to be a little bit more convivial to inclusion?
That's a good question. I don't know. That's something that I don't think we actually ever explored. Our motivation, so these are the definitions for attacking co-inversions are the ones that Hagelin defined.
Yeah, originally, but they are not, like very nice for
they're
Young shape.
Yeah, they're awful. I agree. Terrible. That's a really good question, and one that we actually never explored. We were just, because we were trying to pair it with his formula for Macdonald polynomials, as we'll see at the end. That was the motivation, and so we very much stuck to his definitions. I mean, they're the same rotated by 90 degrees, but whatever. Yeah, that's a really good question. I know we've never explored that, but
No, I know that Searles and Manson has studied a little bit more, like, if we go into that other model, it's so. I'm sorry, that was very technical.
That's a great question. No, that's a really good question, because these suck. The co-inversion triples suck so much. They're terrible. Yeah, that's a good question. Yeah, I'll have to look into it. I don't have an answer because we never really thought about it.
Okay, thank you. Sorry for interrupting.
I have a question too, Nicole, if that's okay.
Yes.
So when we were doing the B lambda from the 4, the lambda was both the shape and the filling that we started off with.
That's exactly it. Yes.
So for in this case so A is the shape, right? And then is lambda the filling, or is A the filling? What's the filling in these cases?
We'll see. I'll do an example.
Okay.
I'll do an example. Yeah. So as I was saying, the combinatorial model for these Demazure crystals, the first thing we needed to do was change the vertex set. We needed to change the set over which we were defining our crystal. And we went from the semi-standard Young tableau, which are very easily defined in fillings of partition shape, to these much more complicated semi-standard key tabloids, which are fillings over composition shapes, right? Where here the composition is a partition times a permutation, essentially. Good. So why do we care about these? Why are these fillings good? Why do we like the semi-standard key tabloids? Well, the first, or one of the reasons, is that we can grade these tabloids, right? And the way we grade them is by a thing called MAJ, or major index. As we'll see, this grading is really nice and really important in relating it to these Macdonald polynomials, or these non-symmetric Macdonald polynomials. So what is MAJ? Essentially, MAJ is a sum over weighted descents of each row. So this is best explained by just doing an example. So what you're going to do is you're going to, believe me that this is a filling that satisfies all these non-attacking co-inversion nonsense. So what you're going to do is you're going to go down each row and you're going to say, all right, whenever I see a number A that is smaller than the one to its right, that's going to be a descent for me. So here, 1 is equal to 1, nothing. 1 is smaller than 4, great. And then what I count is the number of boxes to the right of 4, including 4, which is 1. Then I do the same thing here. 6 is bigger than 5, and so I count 1. And then here there are no more. So that's 1 plus 1 equals 2, right? Then you can do the same thing here. You'll see that it's 2. Now let's do it here. So here we see 3 is bigger than 1. We get 3 because it's 3 boxes to the right of 3. 5 is bigger than 3. So then we get 2 boxes. So that's 3 plus 2 is 5 so far. Then we do the next one. We see that 2 is bigger than 1 and we count a 1. So it's 5 plus 1, which is what gives us 6. And that's basically match. It's very easy to compute. Good. So in order to define a crystal, we need to define operators, right? We have the vertex set. And the way that we define these crystal operators is we basically did the following. So it's a bit more complicated than for semi-standard Young tableau, right? You're not just going to change one entry, you're going to change consecutive rows, and you're not just going to flip one I to an I plus 1, you're going to flip I's to I plus 1s and I plus 1s to I. So you're going to do a double flip at each step. So how does it go? Suppose I have this and I wanted to apply it in E4. So the way I do it is I pair, so 4 is going to change 5s to 4s. So I want to pair 5s with 4s, pair 5 with 4s, and then this one is going to be the one that's unpaired. It didn't pair with anything. So what E4 is going to do is it's going to change all the 5s that are adjacent to this 5 in the same row as that circled 5. So consecutive 5s essentially to 4s, and it's going to change all the 4s that were paired with these 5s to 5s. So it just flips that entire consecutive set of columns. F4 is going to do the same thing but backwards, right? And then so whenever I is basically anything from 1 to n, you're going to end up with what are known as finite edges because you're changing i's and I plus 1s. But we want something that is known as an affine crystal. So we want to add what are known as affine edges, in which case we want to define operators that are going to change 1 and n, right? And essentially we can think of that, if you're familiar with Dynkin diagrams, as just taking the Dynkin diagram for type A and making it an affine Dynkin diagram, which is precisely joining the 1 and the n, so it's a full circle, right? So here for E0, it's an analogous kind of definition. It's a little bit different. So here we want to pair 1s and n's, so in this case n is 5, so we want to pair 1s and 5s, right? But we're not just pairing across columns, we're also allowed to pair across, no, we're not just pairing in the same column, we're allowed to pair across adjacent columns. So there's a formal definition for this. Obviously, I'm just giving you kind of a schematic of it. And then here, once again, you're gonna look for the one that's unpaired, and you're gonna do the same kind of a deal. You're gonna change all the 1s to 5s in these adjacent columns, and you're gonna change all the 5s that were paired to 1s. And that gives you the operators. So they're more complicated because obviously you're gonna have more complicated filling rules. So if you just change one entry, it doesn't work, essentially. You end up with contradictions with respect to these attacking and coinversion conditions. Good. So what do we get once we have these operators defined? Well, we get the following theorem, which is exactly, this is a theorem due to Sammy and myself, which is that these operators, these EIs or FIs, however you want to define them, in this, and including this E0, this affine operator, give you both a finite Demazure crystal structure and an affine Demazure crystal structure when you include the E0s on these semi-standard key tabloids. That is to say that these operators know when to die. So this is answering the first question. What do I mean when I say they know when to die? So let's do an example. Suppose we have W is just our identity permutation. So we should just be getting a crystal that is one vertex, right? It's not we're getting the full crystal and then we're erasing, is the operators should give us just one vertex. What does that mean? That means that on this highest weight, which is the shape has to be 2, 0, 0, because the identity applied to lambda equal 2, 0, 0 is 2, 0, 0. So I draw this shape, I fill it with weight 2, 0, 0, that is this semi-standard key tabloid, and I act by F. But because I should just be getting one vertex, that means that my operator should all act by 0. And that is true. If you go back and actually learn what the definition of these operators are, and you act on this, you'll see that every single operator spits out 0. And so what that's telling you is these operators exactly know what the crystal structure is, the Demazure crystal structure, because they tell you, look, that edge, it's not supposed to be there. You don't have to go back and erase it. You don't have to a priori know what the crystal already is. Right here, if we go one step further and we were to apply an S1 to this intermediate Demazure crystal, Then here, what we're going to look at is we're going to look at lambda equals 2, 0, 0, same highest weight, but now our shape is going to be S1 acting on that. So our shape is going to give us 0, 2, 0. That's our A. That's this shape. And now you'll see that if you act by F1 on this, you don't get 0. You get exactly what you're supposed to be getting. But now if you try to act by F2s, all the F2s here are going to give you 0 because you end up with things that are not well defined. You end up with attacking pieces or co-inversions showing up. So the operators are defined to give you 0 on those cases. And so what that means is that the crystal corresponding to this is exactly the crystal that you wanted, but you didn't have to go back and erase it. Again, that's the key point here. And of course, when you look at the full crystal, right, where you're looking at just S1 times S2, these Demazure operators recover the original story of semi-standard Young tablet. They recover the exact same crystal, nothing is lost, but they give you all the interpolated pieces in between. Does that make sense? Excellent. Now, one of the things that so that answers question 1. The second question was, how do you see this nesting, right? Here, you see that this is supposed to be nested inside of this one, which means that this should show up in here. Now, and this should show up in here, right? And so on. Now, in this case, it's kind of stupid because the boxes are so simple that you can see how one is, fits inside of the other, obviously. The problem arises when, A or lambda is not just one row, but it's multiple rows with multiple sizes. And the A's that you're applying, or the SI's, are flipping these rows around. So your shape is changing. Now, remember that the fillings on these tabloids or whatever depend on the respective length of the fillings and the boxes. So if you're flipping a row, your filling of that shape really is going to get messed up because the previous filling is not necessarily going to work. So the embeddings are not so obvious, right? And so that's the second question that we're going to address. But before that, I forgot basically the whole point of this is that the operators know where to die. So let me just say, because this is important, that this is not the only construction of Demazure crystals that exists. So there is a model for Demazure crystals that predates our model, and that is due to Asaph and Anna Schilling. But however, what they did is it's only for finite Demazure crystals, so ours includes the affine case. And they defined it over, these are, actually, let me just say this, with Maj equals 0. So they defined it over a restricted version of the set that we're dealing with. So ours includes all these graded pieces. For them, their vertices have more conditions on them because you're forcing this major index to also be 0. So in many ways, you can think of ours as just basically a vast generalization of theirs to both the graded setting and to the affine setting. Okay, now that sorry, I forgot to say that. Now let's go back to this embedding, which I was getting at. So how do we realize the embedding? So what we do is we want a map that's going to embed the vertices of shape of one crystal here of W lambda under this action of SI, under the action of the symmetric group, into the crystal where the shape is precisely altered by that SI, right? Which is equivalent to saying we want an embedding from this set of semi-standard key tabloids of shape A into semi-standard key tabloids of shape SI times A, right? And how do we do it? Well, we just define them. I'm going to define them through an example, of course. And so we have two types of embeddings. We have, first of all, an affine embedding and a finite embedding. The finite embedding is going to take something that has shape A, let's say with 7, 5 in rows I and I plus 1. And if we were to apply S3 to it, we would want to flip 5 and 7, right? That's the action of SI on these weak of SN on these weak compositions. So the incredible thing is that this operation could just be defined by acting locally, by just modifying the entries of those two rows, even though the filling conditions are global, right? It's how these two rows interact with every other row above it and below it. If you just take care of making sure that the two local rows behave well with respect to each other, everything works. And what you do is you basically, you flip the shape, right? So you take here 7 moves to row 4, the 5 boxes move to row 5, or row 3, sorry. And then you leave the first 2 entries the same, and then you locally flip a column as you need. So you go through column by column from left to right, and you say, all right, do I need to flip these 2 entries? Yes or no? If you don't need them because of orientation purposes and filling purposes, those 2 rows are fine. With respect to the previous ones, you're good. But if you leave them the same and it causes a problem, then you flip them. And you basically go through and flip them as you need. And that's exactly what happened here. So the red ones are the flipped ones. The black ones are the ones that were good if you just kept them the same. And likewise, for the affine embedding, here, what you want to do is you want to change the topmost and the bottommost row, right? So you make the appropriate changes to the length of the rows, right? Which is basically, you take your first entry and you move it to the end -1. You take your last entry, you move it to the front +1. So this is a very classical action. This is not our work at all. However, the actual action on Tableau is very similar to the finite case, where you just have to flip the entries in those two rows, but instead of flipping across each column, you flip diagonally, right? So here you want to flip across adjacent columns, not necessarily the same column. And it's the same idea. You look at these 2, do I need to pair or flip the 3 and the 5? Yes or no, depending on the local relations. But just the local relations between those 2 rows, and that's the key point. And the amazing part is that just by defining these things locally, everything is good, nothing breaks, and that these embedding operators really do realize the filtration on Demazure crystals, right? So this allows us to take the smaller crystals and embed them into the larger ones by having a perfect bijection between the vertices and preserving these crystal operators that were changing multiple rows and multiple columns simultaneously, right? So let's do an example, just because I have 10 minutes, right? Yeah, okay, good. Let's do a quick example just so that we see it. So what happened here? If we look at 1, 3, 1, right? And we look at, this is an affine crystal because we're including the 0 edges, as you can see. Then if we look at 1, 3, 1 and we act by S0, we should get the crystal corresponding to 2, 3, 0, right? So that's essentially saying this crystal embeds into this one by the action of S0. And what the theorem is saying is that, all right, if you locally apply these embedding operators to this vertex, you get this one. To this one, you get this one. To this one, you get this one, and so on. But not only that, that embedding map commutes with these operators, with the crystal operators that we had previously defined. And that's basically the core of the theorem, that you get this combinatorial realization of the embeddings, which I mentioned at the beginning. Any questions about this? Because at this point, I want to move on to characters and Macdonald polynomials and how this all ties together with that. But I also went a little quickly at the end, so do ask me or interrupt me. Okay. Good. Then let's move on. So characters and Macdonald polynomials. What does this whole story have to do with these polynomials? So maybe you're familiar with them, maybe you're not. There are these things called Macdonald polynomials that show up all over the place. They show up obviously in algebraic combinatorics. They show up in algebraic geometry. They show up in, these days, even knot homology. They're all over the place. And the reason that people really care about Macdonald polynomials, these are symmetric functions, is that they basically generalize a whole slew of families that of symmetric functions that people care about, like Schur functions, Hall-Littlewood functions, Jack symmetric functions, etc. So these are great, people really like them, but it turns out that there's a further generalization of these Macdonald polynomials, and they're known as nonsymmetric Macdonald polynomials. So these were originally introduced by Optum and Macdonald and then generalized by Cherednik, and they're indexed just like our Demazure crystals by weak compositions. They're not indexed by partitions. Moreover, when you specialize A to be the reverse of a partition lambda, so a partition going in the opposite direction, then you get the symmetric Macdonald polynomials back. So they encode all the theory that you want for the symmetric story, but then way more. And they're not symmetric, as the name suggests, right? Now, these polynomials were not, or these functions were, well, yeah, polynomials were not defined combinatorially initially. They were defined, using Dunkel operators and whatever else. However, in a really remarkable result due to Hagelin, Heyman, and Lohr, they came up with a combinatorial formula for these polynomials, right? That are in their polynomials in variables x1 through x whatever infinity, and then you have parameters q and t. Now they came up with a combinatorial formula for all three variables. Beautiful, in terms of fillings of boxes, just like we were dealing with before. Now, I'm not going to give you the full formula. I'm just going to give you the formula when you specialize t equal to 0, because that's the case we care about here in this talk. And when you specialize t equal to 0, their formula reduces to the following. So it's a sum where the q, it has coefficient major index of t. So this is this MAJ that we were seeing before, and x to the weight, where weight is just like we were dealing with before, right? The weight of where you just take the associated monomial to each tableau. And then you'll see that the sum, the indexing set, is precisely the set that we had in our Demazure crystals. So maybe, once you start seeing this, you're like, oh, look, given our construction, then hopefully it's natural that the following theorem, kind of follows. So this is a theorem due to Asif and myself as well, which is basically telling you that these specialized non-symmetric Macdonald polynomials are characters of a finite graded sum of finite Demazure crystals. I'll do an example, and that statement will make a lot more sense. So this was previously known by Asif. She proved it using something else. But the key point here is that we actually got an explicit formula for that expansion, right? So saying that this is the character of a finite graded sum of Demazure modules is equivalent to saying that EA can be written as a positive sum of key polynomials or as a positive sum of Demazure characters, right? That's exactly this. So we not only know that it can be done, we know exactly how to do it, where these coefficients are exactly going to be these major index statistics, right? So this is kind of mimicking, it's refining, or not refining, it's reordering the sum given by Hagelin, Heyman, and Lohr, but into pieces where we know exactly what the Demazure characters showing up are. If you're more familiar with the symmetric story, this you can think of as essentially a non-symmetric analog of the Schur expansion of Hall-Littlewood polynomials. That is because when you specialize t equal to 0, these are really non-symmetric analogs of the Hall-Littlewoods, and these key polynomials are non-symmetric analogs of Schur functions, much like these are non-symmetric analogs of the symmetric Macdonald polynomials. So let's do an example to talk about what this theorem is saying. So suppose I want to find what the key expansion is for E131. How would I do this? So I'm going to look at A equals 131, and I'm going to look at the highest weight tableaus of shape 131, right? And this is going back to your question around, what are the weights that I'm looking at? I know the shape, what are the weights? So here, this tableau has weight so yeah, you can see the weights here are not at all weight lambda, right? One of them is and one of them is not. But this doesn't take a lot of effort to actually find what the highest weights are. You just, once you familiarize yourself with the operators, it takes you maybe 2 minutes or a minute to just jot down some examples and say, oh yeah, these are the only fillings that are good. So the way you do this is you come up with these two things. Okay, here they are. Then you generate the corresponding crystals by acting on them I really should say here, finite. You don't need the affine ones for this. You really just act on them by these finite crystal operators. You generate the green piece, you generate the yellow piece, and then all you need to do is, well, you take their characters. And really, you don't even need to take the character of the whole thing. You just take the character of the lowest weights that are showing up. Why? Because that's exactly what's going to give you the key expansion. This is going to be the crystal that corresponds to the key polynomial indexed by 1, 2, 2. Why 1, 2, 2? Because that is the weight of this lowest thing showing up. This is going to be the character of this Demazure module, or this Demazure crystal. But this Demazure crystal is indexed by this lowest weight, which is weight 131. and that's this. The major index is going to give you exactly what these Q coefficients are. And it's a theorem that these finite edges preserve the major index. So the major index of this is going to be the same as this, is going to be the same of this. And that's why it's consistent. It doesn't matter which one you take. So this green one you can compute has mag equal 1. The yellow one has mag equal 0, and that gives you these coefficients. And that's all there is to it.
Question, is
Yes.
it clear that there's going to be a unique lowest weight?
No, that is a fantastic question. In fact, there is not. What there is, so a Demazure crystal has many lowest weights, but it has a unique lowest weight. So it can have like a bunch of, it's like if you think of like an upside down tree, it can have like a bunch of dangling edges, but there's always one unique one that is lowest than all the other ones. And that unique lowest weight is precisely going to have weight equal to precisely this, like the reverse of the highest weight.
So can you think of this lowest weight as the one where your composition is kind of like the highest? So basically just everything is as shifted to the right as possible?
The composition is the highest. Yes, because it's associated to the word that is longest inside that crystal. So if you take that crystal and say, what is the longest word I can generate inside this crystal? That longest word is exactly what's going to index your lowest weight. Yes.
All right, cool.
Thank you. Okay, and so then one more example, because it doesn't hurt. What if we wanted the explicit key expansion of E230? Same idea. You generate these highest weights, right? For shape 230, you generate this one, this one, this one, and this one. You act by your operators. You see that, you know, this is going to be the lowest weight corresponding to this one. This one didn't go anywhere. This one is the lowest weight, and then this one is the lowest weight. And then these entries, these weights are just going to be the weight of this one, this one, this one, and this one, just the lowest weights. And then, of course, the Q coefficients are going to be the mag of the corresponding pieces. So it's the same idea over and over and over again. And computationally, it's actually very easy when you, like I said, you have to do a couple of examples to get the hang of it, but the operators are actually not that hard once you've done a few of them. Great. And then now you'll notice that this is, you know, I have these purple edges connecting this. So you might say, all right, so far we haven't really used the affine edges. They're just there as decoration. But what you hopefully notice by these two examples is that each of these finite pieces are always conjoined to the other ones through an affine edge. So you're always going to get a big one, just one connected piece once you add the affine edges. It's one connected affine crystal. Even though this decomposes into a bunch of finite, like individual finite pieces, they are all grouped together through the finite edges to one affine crystal, right? And that's a theorem that was already known. So I'm going to jump theorem 2 and go to theorem 3, and then I'll come back to theorem 2. A consequence of this construction is that we get a purely combinatorial proof that these nonsymmetric Macdonald polynomials, these specialized nonsymmetric Macdonald polynomials, are the characters of an affine Demazure crystal. So this was known already in the case for modules, so therefore known for crystals as well. This was due to Sanderson and Bogdan-Eon, but this was proven not combinatorially, so this gives us a nice, very explicit combinatorial proof. And then as a nice side effect, we get a nice new formula for these, what are known as the non-symmetric Kotzka-Folkes polynomials. Since these are specializations of the symmetric kind, we also get a new formula for the symmetric Kotzka-Folkes polynomials, which are the coefficients of in the Schur expansion of the Hall-Littlewood polynomials. So these are known as KABs in terms of mag. Essentially, it allows us to write these polynomials as the sum over Q to the major index. Why is this nice? Well, we already had a combinatorial formula before for these polynomials, but it was in terms of a statistic known as charge, which is a lot more complicated than counting descents. So this is nice because it's just very simple and very straightforward to actually just sum over mag. It's very easy. And that's pretty much it. I'm right on the dot, so I'm not going to go into the details of the proof. So I'm just going to skip this last talk, and if you have any questions, I'm happy to go into it. Thank you.
Awesome. Let's thank the speaker.
Wow, we got a clapping noise. This is awesome.
Well, there was like 1 million people who showed up, yeah? So it's everyone just clapping together.
This is a lie, but I want that soundtrack so much.
Are there any questions? Yes, Mike, you can unmute yourself and just ask.
So is there any indication of what this is about Macdonald, the non-symmetric Macdonald polynomials at other values of t or arbitrary t?
This is actually, no, that's a good question. And I don't think so. And we thought about whether we could generalize this. But I honestly don't think that this is an avenue for that. The reason for that is that if you look at the original formula by HHL, right, for t, the part that's missing here, I didn't write it, but I'll just write it right now. So what you get if you let this just be t, you get a sum over some sort of rational thing where you have t's and q's here, and you have t's and q's here, or maybe you have only t's on the top. But the point is that this extra piece is a rational function. And so you're not going to end up with some sort of nice linearity, which means that if you're trying to translate it to some sort of modular crystal structure, you need integrality to be there. And this is absolutely not integral. And so it completely messes up any construction that we would hope to have. So if it's possible, I don't think it's possible through crystals. Somebody recently, proposed or asked me if I could do this with some sort of modified integral version of this formula, where maybe this is linearized. Potentially, I haven't looked into it. But this construction by itself, yeah, we thought about it, and I don't know how to interpret rational functions or rational numbers essentially in a module theoretic way. Yeah.
Okay.
Yeah.
Are there other questions? Or
I was gonna say, maybe allow me to say one thing that something that we might have hope for. And again, I haven't actually looked into this, but I have talked to this. I've briefly talked about this with a couple of people. Is the idea that even though we don't have a formula for these in other types, we just have a formula in type A. The notion of a crystal makes sense in other types. So potentially we could try to take this Demazure crystal construction and generalize it to another type, and from that kind of back construct the combinatorial formula for these Macdonald polynomials and other types, which makes sense algebraically. They make sense crystal theoretically. We just don't have an explicit formula. So that's a direction that potentially has a lot of hope, but I haven't looked into it explicitly. So.
Are there any other questions? If not, let's thank the speaker again. Yeah.